Welcome to the Deep Dive. In a world constantly throwing information at us, it's easy to feel overwhelmed.
It really is.
Our mission here is simple. You bring us a stack of sources, articles, research, notes, and we plunge in to pull out the most important nuggets, the, surprising facts, and the fundamental insights that actually help you cut through the noise and feel truly well-informed.
And today, you've given us a fantastic source to explore. It's this comprehensive text that tackles a huge range of physics topics.
Yeah, and honestly, right from the start, this source grabs your attention. I mean, it opens with the Constitution's preamble and the national anthem. It's a fascinating choice to frame physics.
It really is. It almost suggests a parallel, doesn't it, between the principle structuring society and the laws structuring reality. So our deep dive today is to navigate all this information, pull out the core concepts, and crucially, use the specific examples the text provides.
To make it clear.
Exactly. To show you how these powerful ideas pop up everywhere, we're basically going on a journey guided by this text from, everyday motion down to atoms and nuclei and even the stuff inside your phone.
Okay, let's dive in, starting with motion. But let's get specific things that spin or move in circles.
Right, circular motion.
When something moves in a circle, even if its speed is steady, its direction keeps changing.
And any change in velocity, even just direction, means acceleration. That's centripetal acceleration, always pointing towards the center of the circle. Now, if the speed also changes, that's tangential acceleration along the path. And the force causing that centripetal acceleration, that's the centripetal force.
The text gives some great examples here.
It does, like the well of death motorcycle stunt.
Oh, yeah, where they ride horizontally inside a big cylinder. How does that work?
Okay, so the wall pushes in on the tires, that's the normal force, and it provides the centripetal force needed to keep turning.
Right, pushes them into the circle.
But gravity's pulling down. So to stop sliding down the wall, you need friction pointing up. Static friction between the tires and the wall.
So the wall pushes them in, friction holds them up. The text mentions a minimum speed, though. Why?
Well, if you go too slow, the inward push needed, the normal force, is smaller. And the maximum static friction you can get depends on that normal force.
Okay.
So too slow means not enough potential friction to fight gravity. You slide down. At the minimum speed, the friction is just maxed out balancing gravity, and the normal force is doing its job keeping you in the circle.
Fascinating. Physics making sense of daredevil stumps. Another example from the text, banking roads.
Oh yeah, crucial civil engineering. On a flat curve, it's mostly friction providing the centripetal force.
Which isn't always reliable.
Exactly. Banking tilts the road. Now, the normal force from the road isn't straight up, it's tilted inwards.
So part of it points towards the center of the curve.
Precisely. That horizontal component helps provide the centripetal force, reduces the need for friction, especially at one particular ideal speed for that bank angle.
But cars go faster or slower than ideal. The text says friction still matters.
It does go slower than ideal, and you tend to slide down the bank. So friction acts up the slope to help keep you turning.
Okay.
Go faster, and you tend to slide up the bank. Friction acts down the slope, again helping provide the needed inward force. So banking sets the stage, but friction defines the upper and lower safe speed limits.
Right. Okay, sticking with circles, but vertically. Whirling something on a string versus a rigid rod. What's the key difference the text highlights?
It's all about tension versus compression. A string can only pull, it has to stay taut.
Right.
At the very top of the circle, gravity is pulling down. The string also has to pull down towards the center to provide the centripetal force. If the object isn't moving fast enough, the required inward force is less than gravity, and the string just goes slack.
No more circular motion.
Nope. But a rigid rod, it can push or pull. At the top, even if the object is moving slowly, the rod can actually push down, providing the necessary centripetal force along with gravity, or even opposing gravity slightly if needed. It doesn't go slack.
So it can maintain the circle even at very low speeds at the top.
Theoretically, even zero speed momentarily at the very peak.
That's a neat distinction.
Yeah.
Okay, so spinning things have energy too. Rotational energy.
Yep, rotational kinetic energy. Just like linear motion has kinetic energy 12 millimeters squared. Rotation has 12 I omega squared. Omega is angular velocity, how fast it's spinning, and I is the moment of inertia.
Moment of inertia. That's like the rotational version of mass. harder to spin.
Exactly. It measures an object's resistance to changes in its rotation. The text defines it as the sum of Mr. squared for all the little bits of mass making up the object relative to the axis.
So mass further out counts more.
Much more because of the r squared. The text uses a uniform ring as an example. All the mass m is at the same distance r, so its moment of inertia is just mr squared.
And torque is the rotational equivalent of force.
You got it. Torque causes angular acceleration, alpha. The rotational equivalent of FMA is tau equals I alpha.
Makes sense. And there's angular momentum, too.
Right. Analogous to linear momentum, MV, angular momentum is L equals I omega. And just like linear momentum is conserved if there are no external forces.
Angular momentum is conserved if there's no external torque.
Perfect. That's the figure skater explanation. Pull arms in, decrease I, so omega has to increase to keep L constant. The text mentions this, and also rolling motion, which is a mix of spinning and moving forward.
It's amazing how these few rotational ideas explain so much, from planets to playground swings. Okay, let's shift from solid objects to, well, squishier stuff, fluids.
Liquids and gases. The text points out we often just say fluid for liquids like brake fluid, but air in your brake fluid, that's bad.
Definitely bad. So fundamental property of fluids, pressure.
Pressure, force per unit area, acts in all directions inside a fluid. Atmospheric pressure is the classic example, just the weight of all the air piled up above us.
And it changes with height, the text reminds us.
Yeah, less air above you, higher up, so lower pressure, why your ears pop. The text estimates the air column height at sea level is roughly 8 kilometers.
And it gives a simple calculation pressure from a 50-kilogram student standing.
Yeah, just to ground the concept, estimate their foot area, maybe 500 square centimeters, convert that to square meters, 0.05.
Okay.
Their weight is force, about 50 kilograms times 10 meters squared, so 500 newtons. Pressure is force divided by area, 500 over 0.05, that's 10,000 pascals.
Straightforward. What about surface tension? Why do water droplets try to be spheres?
That's all about cohesive forces, molecules pulling on each other. Inside the liquid, a molecule is pulled equally all around.
Okay.
But at the surface, molecules are pulled by neighbors below and sideways, but not much from above in the air, so there's a net inward pull.
Trying to pull the surface tighter.
Exactly. The liquid minimizes its surface area for a given volume, and the shape that does that, a sphere. The surface acts like a stretched elastic membrane.
And this causes other effects, like pressure inside drops.
Yes, excess pressure. Inside a liquid drop, the pressure is slightly higher than outside because the surface tension is squeezing it. Inside a soap bubble, which has two surfaces, inner and outer film, the excess pressure is double that of a drop the same size.
And capillary action. Water climbing up a thin tube.
That's linked too. It's an interplay between cohesion, liquid sticking to itself, and adhesion, liquid sticking to the tube walls.
Right.
If adhesion is stronger, like water on clean glass, the water wets the glass, the surface curves up at the edges, concave meniscus, the contact angle is small, and surface tension pulls the liquid column up.
And if cohesion wins? Like mercury.
Like mercury on glass, yeah. It doesn't wet the surface, the meniscus curves down, convex, contact angle is large, and the liquid level in the tube is actually pushed down. The text has a calculation for mercury, finding the contact angle from how much it's depressed.
That's pretty neat. And the text drops a bombshell. Einstein's first paper was on capillarity.
Isn't that amazing? It just shows you even the greatest minds often start by deeply investigating seemingly simple fundamental phenomena. It's not always relativity right out of the gate.
True. Okay, from static fluids to moving fluids, hydrodynamics, ideal fluids.
That's the physicist's starting point simplify. An ideal fluid is incompressible, density doesn't change, and non-viscous, no internal friction. Real fluids aren't quite like that, but the ideal model gives us key insights.
Like different types of flow.
Yeah, streamline or laminar flow is smooth, orderly, like layers sliding past each other. Think slow river flow. Turbulent flow is chaotic, swirling with eddies, like rapids or water blasting from a faucet.
And viscosity is that internal friction you mentioned.
Pretty much. Resistance to flow. In liquids, it's mostly molecules attracting each other. In gases, it's more about molecules bumping into each other as layers move at different speeds. The text mentions the velocity gradient, how speed changes between layers.
Okay. And terminal velocity. Why does a raindrop stop accelerating?
Ah, right. As something falls through air, or any fluid, three forces act. Gravity pulls down, buoyancy pushes up slightly, and viscous drag pushes up, opposing the motion.
And drag increases with speed.
Exactly. So as the object speeds up, the drag force gets bigger. Eventually, the total upward force, buoyancy plus drag, equals the downward force, weight. Net force is 0.
So no more acceleration, constant speed.
That's terminal velocity. The text shows the forces balancing for a falling sphere.
Conservation laws apply to fluids too, right? Continuity and Bernoulli.
Absolutely. The equation of continuity, A1V1 equals A2V2, is basically conservation of mass for incompressible flow. Where the pipe narrows, area A decreases, the speed V must increase.
Like pinching a hose.
Exactly. And Bernoulli's principle is conservation of energy applied to fluid flow. It connects pressure, speed, and height. The big takeaway is usually that where the fluid speed is high, the pressure is low, and vice versa, assuming height doesn't change much.
The text calculates pressure drop in a pipe constriction.
Yeah, showing that inverse relationship directly. High speed in the narrow part, lower pressure there.
Yeah.
It's fundamental to how airplane wings work, among many other things.
Okay, let's shift gears completely. From macroscopic flow to the microscopic world of gases and heat. Kinetic theory.
This is a brilliant approach. You make some simple assumptions about gas molecules. They're tiny, numerous, move randomly, collide elastically.
Like tiny billiard balls bouncing around.
Sort of, yeah. And using statistics on this simple model, you can connect the microscopic behavior, like the average kinetic energy of the molecules, to the macroscopic things we measure, like temperature and pressure.
And the key connection is?
Temperature. The absolute temperature of a gas is directly proportional to the average translational kinetic energy per molecule. Hotter gas means faster moving molecules on average. That En proportional to T is huge.
The text also mentions degrees of freedom.
Briefly, it's about the different ways a molecule can store energy moving side to side, up and down, forward, back, that's translational, but also rotating or vibrating. Equipartition theorem says, basically, energy gets shared out equally among these available ways, these degrees of freedom, when the gas is in equilibrium.
Okay, how does this energy actually move around? Heat transfer.
3 ways: conduction, convection, radiation. Conduction is direct contact molecule to molecule transfer, like heat moving up a metal spoon in hot soup.
Got it.
Convection involves the movement of the fluid itself, hot air rising, hot water circulating. It carries the thermal energy with it.
Like a radiator heating a room.
Exactly. And radiation is totally different. It's energy traveling as electromagnetic waves. Doesn't need a medium. That's how the sun's heat gets to us through empty space.
Let's focus on that thermal radiation.
Okay, anything with a temperature above absolute 0 emits thermal radiation. It's caused by the thermal jiggling of charged particles within the object. Hotter objects jiggle more, radiate more.
The text talks about a perfect black body.
This sounds weird. It's an ideal concept. A perfect black body absorbs all radiation that hits it at any wavelength, nothing reflected.
Okay.
And the flip side is, it's also the best possible emitter of thermal radiation for any given temperature. The text describes Ferri's black body as a way to approximate this. Imagine a hollow sphere with a tiny hole, maybe coated black inside.
Right.
Light goes in the hole, bounces around, gets absorbed with each bounce. Almost none gets back out. So the hole acts like a perfect absorber. And if you heat the sphere, the hole radiates like a perfect emitter.
Clever. And the Stefan Boltzmann law quantifies this radiation.
Yes. It says the total power radiated per unit area from a black body is proportional to the absolute temperature raised to the 4th power, R proportional to T to the 4th.
Wow. 4th power. So doubling the temperature increases radiation 16 times.
Exactly. It's a very strong dependence. Real objects aren't perfect black bodies, so there's an emissivity factor, E, between 0 and 1, multiplying that. R equals E sigma T to the 4th. Sigma is just a constant.
Explains why hot things glow so brightly and why dark clothes feel hotter in the sun, that are absorbers and emitters. Yeah. Okay, on to the really big rules. Thermodynamics.
The laws governing energy, heat, work, and what transformations are possible.
Starts with the Zeroth law. Why 0? Seems like an afterthought.
It kind of was. Its fundamental importance was realized after the first and second laws were already named. It defines thermal equilibrium. If A is in equilibrium with C and B is in equilibrium with C, then A and B must be in equilibrium with each other.
Obvious, maybe.
Seems so, but it establishes that temperature is a valid concept. It's the thing that's equal when systems are in thermal equilibrium. It allows thermometers to work consistently.
Okay, temperature established. Then the first law.
Conservation of energy, basically, applied to heat and work. It says the change in a system's internal energy, delta U, equals the heat Q added to the system minus the work W done by the system. Delta U equal QW.
Internal energy is just all the molecular energy inside.
Pretty much. Kinetic and potential energy of all the molecules. So if you rub your palms, you do work on them, W is negative, maybe no heat flows, Q0. So delta U is positive internal energy increases, they get warmer.
Or heat an engine cylinder, Q
Yeah.
positive. The gas expands and pushes a piston, W positive. And the internal energy might change too.
Exactly. The text outlines different processes. Isobaric is constant pressure. Isochoric, constant volume here, no work is done, W0. So any heat added just increases internal energy, delta U do.
Isothermal.
Constant temperature. For an ideal gas, internal energy only depends on temperature, so delta U is 0. This means all the heat added must go into work done by the system, QW.
And adiabatic.
No heat exchange at all, Q0. So any change in internal energy comes from work being done. Delta U equals now to W. If the gas expands adiabatically, it does work, loses internal energy, and cools down.
Free expansion is mentioned as a special adiabatic case.
Yeah, it's weird. A gas expands suddenly into a vacuum, no external pressure, so no work done, W0. It happens fast, so no heat transfer, Q0. First law says delta U equals QW equals 0. Internal energy doesn't change. For an ideal gas, that means temperature doesn't change either, even though the volume increased dramatically.
Strange. These laws obviously govern engines and refrigerators.
Fundamentally, heat engines take heat from a hot source, convert some to work, and dump the rest to a cold sink. Refrigerators use work input to force heat to flow from cold to hot.
Then the second law steps in and says, you can't win.
Huh. Sort of. It sets limits and defines the direction of things. It introduces entropy, a measure of disorder. One version, the Kelvin-Planck statement, says it's impossible to build an engine that takes heat and converts it all into work in a cycle. Some heat must be wasted, rejected to a cold reservoir. 100% efficiency is impossible. Another version, the Clausius statement, says heat doesn't spontaneously flow from a colder body to a hotter body. You need to put work in to make that happen. That's your refrigerator. The text shows the energy flow diagram for a fridge, emphasizing that work input.
So limits on efficiency, the direction of heat flow, that's the second law. The text mentions the Carnot engine briefly.
As the theoretical ideal, the most efficient possible engine operating between two given temperatures. Real engines always fall short.
Okay, let's move to things that repeat, that oscillate. Simple harmonic motion.
SHM. The simplest, most fundamental type of oscillation. It happens when you have a restoring force that's directly proportional to the displacement from equilibrium and always points back towards equilibrium.
Like a mass on a spring, Hooke's law, F-A-K-X-E.
The classic example. The minus sign shows the force opposes the displacement.
And its motion has specific properties.
Yes. Velocity is 0 at the extreme ends of the motion and maximum as it passes through the equilibrium point. Acceleration is the opposite. Maximum at the extremes, where force is max, and 0 at equilibrium, 0 net force. The text shows the nice sine-cosine graphs for position, velocity, acceleration over time.
What about energy in SHM?
Constantly swapping between kinetic and potential energy. At the extremes, all potential energy, spring stretched compressed. At equilibrium, all kinetic energy, moving fastest.
Well, the total stays the same.
If there's no damping, yes. Total mechanical energy, 12 mV2 plus 12 kB2, is conserved. It depends on the mass, the frequency, and the square of the amplitude, maximum displacement.
The simple pendulum is often used as an example.
It is, but it's only approximately SHM, and only for small angles of swing, the text says usually less than 20 degrees or so.
Why only approximate?
The restoring force isn't exactly proportional to the displacement, the arc length, but rather to the sine of the angle. For small angles, sine theta is very close to theta itself in radians, so it behaves like SHM.
And its period, the time for one swing.
Famously, T equals 2 pi times the square root of L over G. Length L of the pendulum, G is gravity. Importantly, for small angles, it doesn't depend on the mass or the amplitude. The text shows an example of how the period changes if length changes slightly.
The text mentions angular SHM too.
Just the rotational version. Instead of force proportional to displacement, you have a restoring torque proportional to angular displacement, like a torsional pendulum or a magnetic dipole oscillating in a B field.
Okay, and resonance, that sounds important.
Hugely important. Resonance happens when you drive an oscillating system at its natural frequency, the frequency it wants to oscillate at anyway.
Like pushing a swing at just the right moment.
Exactly. Energy gets transferred really efficiently, and the amplitude of the oscillations can grow very, very large. The text uses coupled pendulums swing one, and another of the same length starts swinging wildly. It's key to musical instruments, but also dangerous in structures like bridges collapsing if wind excites their natural frequency.
Right, the Tacoma Narrows Bridge story. Okay, from oscillations to waves, how energy travels.
Waves are disturbances carrying energy through a medium or space. Two main types the text introduces: transverse and longitudinal.
Transverse is like shaking a rope. Up and down motion, wave travels sideways.
Perfect example. Particle motion is perpendicular to wave direction. Light waves are transverse. They have crests and troughs.
And longitudinal.
Particle motion is parallel to wave direction, like pushing a spring back and forth. Sound waves are longitudinal. They have compressions, bunched up areas, and rarefactions, stretched out areas.
The text notes where they can travel.
Yeah, transverse waves generally need a rigid medium that resists shearing like solids, or the surface of a liquid. Longitudinal waves just need compressibility, so they travel in solids, liquids, and gases.
What happens when waves meet? Superposition.
Yes, the superposition principle. When waves overlap, the total displacement is just the vector sum of the individual wave displacements at that point in time.
Leading to interference.
Right. Constructive interference if crest meets crest, bigger wave. Destructive interference if crest meets trough, smaller wave. Or even cancellation if amplitudes match. The text shows diagrams of pulses adding up or canceling out.
And standing waves. They look like they're not moving.
They arise from the superposition of two identical waves traveling in opposite directions, usually due to reflection from boundaries. You get fixed points of zero motion called nodes, and points of maximum vibration called antinodes. They're crucial for musical instruments. The allowed frequencies correspond to fitting different standing wave patterns onto a string or into an air column.
Okay, now let's focus on light waves. The historical debate.
Yeah.
Particle or wave?
Yeah, a long debate. Newton favored particles, corpuscles. Huygens proposed a wave theory, which beautifully explained reflection and refraction using wavefronts spreading out. For a long time, the wave theory seemed dominant.
But we now know it's an electromagnetic wave.
Correct. Part of a vast spectrum, from radio waves to gamma rays. Visible light is just the tiny slice our eyes detect, roughly 400 to 700 nanometers wavelength. Different wavelengths give different colors. The text mentions dispersion, how prism splits light, because refractive index depends slightly on wavelength.
And polarization, that's specifically a wave thing, right?
A transverse wave thing. It refers to the orientation of the wave's oscillations. For light, it's the direction of the electric field vibration.
So unpolarized light vibrates randomly.
Randomly in all directions perpendicular to travel. Plain polarized light has vibrations confined to a single plane. Polarizing filters work by only letting through light polarized along a specific axis.
Like sunglasses cutting glare.
Exactly. Glare from horizontal surfaces like water or roads is often strongly horizontally polarized. Vertical polarizers block that. The text gives Malice's law for intensity through a polarizer and Brewster's law for polarization by reflection.
Light also interferes and diffracts, just like other waves.
Definitely. Young's double-slit experiment is the classic proof of light's wave nature. Through interference, coherent light through two slits creates alternating bright and dark bands on a screen.
Bright is constructive, dark is destructive.
You got it. Diffraction is the bending or spreading out of waves as they pass through an opening or around an obstacle. You see diffraction patterns from single slits too.
And this limits how well we can see fine details. Resolving power.
Yes, diffraction fundamentally limits the resolution of any optical instrument. A lens can't focus light to an infinitely small point. It creates a small diffraction pattern, like an airy disk. Resolving power is the ability to distinguish two close together objects as separate.
Depends on
Wavelength of light and the size of the aperture, the lens or mirror opening. Shorter wavelengths or larger apertures give better resolution, let you resolve finer details. The text discusses this for microscopes and telescopes, and how immersion oil helps microscopes.
Explains why electron microscopes are so powerful. Electron wavelengths are tiny. Okay, let's shift to electricity, starting with static charges. Electrostatics.
Studying charges at rest, and the forces, fields, and potentials they create. Potential energy is the energy a charge has due to its position in an electric field. Potential is just potential energy per unit charge.
And equipotential surfaces.
Surfaces where the potential is the same everywhere, like contour lines on a map, but for voltage. No work is done moving a charge along an equipotential surface. Importantly, electric field lines always cross equipotential surfaces at right angles.
Okay. The text moves on to dielectrics,
Yeah.
insulators.
Yes, materials that don't conduct electricity easily. But when you put them in an electric field, their molecules can polarize the positive and negative charges within each molecule shift slightly.
Creating little dipoles.
Exactly. This internal polarization actually reduces the net electric field inside the dielectric material.
Which is useful for capacitors.
Very useful. Capacitors store charge and energy. The basic parallel plate capacitor's capacitance, its charge storing ability, depends on the plate area and the distance between them.
And what's between them?
Right. Putting a dielectric material in between increases the capacitance. Because it reduces the internal field, you can store more charge on the plates for the same voltage. The text notes that even inserting a conducting slab affects capacitance.
Displacement current gets a mention here, too. Seems ahead of its time for electrostatics.
It is a bit of a look ahead. It's Maxwell's idea. Even if no actual charge flows across the gap in a capacitor, a changing electric field in that gap acts like a displacement current. It's crucial for understanding electromagnetic waves and how circuits connect to them.
Right. And electrostatic shielding. Faraday cages.
A practical consequence. If you have a hollow conductor, any external electric field makes the free charges in the conductor rearrange themselves on the surface. They move until the field inside the conductor is exactly zero.
So the inside is shielded.
Completely shielded from external static fields. That's why being inside a metal car during lightning is relatively safe, as the text points out. The charge flows around the outside.
And the Van de Graaff generator. Those things that make your hair stand on end.
Classic electrostatics demo. Uses a moving belt to continuously carry charge up to a large metal dome. Key principle. Charge added to a conductor always goes to the outer surface, so you can keep piling charge onto the dome, building up a huge voltage.
Until the air breaks down and sparks fly.
Exactly, limited by the dielectric strength of air.
Okay, from static to moving charges, current, electricity, and circuits. Kirchhoff's laws seem essential.
Absolutely fundamental for analyzing circuits. They're based on conservation principles.
First one, the junction rule.
Conservation of charge. Whatever current flows into a junction, a point where wires meet, must flow out. Sum of currents in equals sum of currents out.
Makes sense. And the loop rule.
Conservation of energy. If you go all the way around any closed loop in a circuit, the sum of all the voltage rises and drops must be zero. You end up back at the same potential you started with. Using these two rules lets you solve for currents and voltages in quite complex networks.
The text highlights some specific measurement tools based on these principles. The Wheatstone bridge.
A clever circuit for precisely measuring an unknown resistance. You adjust known resistances until a galvanometer, a sensitive current meter, in the middle reads 0. The bridge is balanced.
What does balance mean?
It means the potential is the same at the 2 points the galvanometer connects. When balanced, the ratios of resistances in the arms are equal, PQ equals RX, so you can calculate the unknown X. The text mentions it's used in things like strain gauges.
And the meter bridge is a simpler version.
Yeah, a practical lab version using a meter-long wire of uniform resistance as 2 arms of the bridge. You slide a contact along the wire to find the balance point. Simple and effective.
What about the potentiometer?
A really versatile and accurate instrument. It measures potential difference, voltage, by comparing it to the known potential drop along a uniform wire. Its big advantage is that when balanced, it draws no current from the voltage source being measured.
Unlike a regular voltmeter.
Right, which always draws a little current, potentially affecting the reading. The potentiometer finds a null point where currents balance, giving a very precise measurement. The text shows how to use it to compare amps of cells or find a cell's internal resistance.
Essential lab tools. Okay, now connecting electricity to magnetism. Oersted's discovery.
The big breakthrough. Oersted found that an electric current creates a magnetic field around it. Electricity and magnetism are linked.
And magnetic fields push on moving charges. The Lorentz force.
Exactly. The force F on a charge Q moving with velocity v in a magnetic field B is given by F equals Q times V cross B. It's proportional to charge, speed, field strength, and the sign of the angle between V and B. Crucially, the force is perpendicular to both V and B.
Which means it changes direction, not speed.
Right. Magnetic forces do no work on free charges. Since current is just moving charge, there's also a force on current-carrying wires in a magnetic field. The text uses vector cross products for the directions and mentions units, Tesla, T, and Gauss, G.
How does a charge move under this perpendicular force?
If V is perpendicular to a uniform B field, the force is constant in magnitude and always at right angles to V. That's the recipe for uniform circular motion. The magnetic force acts as the centripetal force.
Like in a cyclotron.
Yes, cyclotrons use this. If V has a component parallel to B as well, the particle spirals circular motion combined with steady motion along the field lines. Helical path.
How do we calculate the magnetic fields created by currents?
Two main tools presented. The Biot-Savart law lets you calculate the field contribution from a tiny piece of current-carrying wire, then you integrate over the whole wire. It's fundamental, but can be mathematically complex.
And the other?
Ampere's circuital law, more useful when there's symmetry. It relates the line integral of the magnetic field around a closed loop to the total current enclosed by that loop. Great for finding the field of long, straight wires, solenoids, coils, and toroids, donut-shaped coils.
The text gives the solenoid formula.
Yeah, inside a long solenoid, the field is uniform and given by B naught times N times I, where N is turns per unit length and I is the current. Very useful result.
Electric motors, loudspeakers, particle accelerators all rely on these forces and fields. Now, how do materials themselves respond to magnetism?
It all comes down to the electrons in the atoms. Electrons orbiting the nucleus and also having an intrinsic spin both create tiny magnetic dipole moments. In most materials, these are randomly oriented.
But they react to an external field.
Yes. We use concepts like magnetic field intensity, H, which is related to the external field, and magnetization, M, which describes how strongly the material itself becomes magnetized in response.
So the field inside is a combination.
Exactly. The total magnetic field B inside is B equals mu naught, H plus M. We also define magnetic susceptibility, Chi, where M equals GH, measuring how susceptible it is to being magnetized, and permeability, mu, where B equals mu H, measuring how well the material supports the field.
And materials fall into different categories.
Three main ones. Diamagnetic materials are weakly repelled by magnetic fields, small, negative Chi. Paramagnetic materials are weakly attracted, small, positive Chi. And ferromagnetic materials are strongly attracted, large, positive Chi.
Ferromagnets are the magnetic ones we usually think of. Iron, nickel, cobalt. What makes them special?
They have magnetic domains. These are tiny regions, microscopic, where the atomic magnetic moments are already strongly aligned with each other, even without an external field.
Like tiny magnets inside.
Sort of. When you apply an external field, domains already aligned with the field tend to grow, and moments in other domains can rotate to align with the field. This leads to a very large overall magnetization. The text notes this disappears above the Curie temperature.
The hysteresis loop sounds important for ferromagnets.
It is. It's a graph of B inside the material versus the applied H as you cycle H up and down. It shows the material remembers its magnetic history.
How so?
The curve doesn't retrace itself. Key features are retentivity, how much B remains when H is 0, and coercivity, how much reverse H is needed to bring B back to 0. The area inside the loop represents energy lost as heat during each magnetization cycle. The text compares this to mechanical hysteresis.
This loop tells you if it's good for a permanent magnet or an electromagnet.
Precisely. Permanent magnets need high retentivity and high coercivity. They stay magnetized strongly and resist demagnetization. Electromagnets, like in cranes or bells, need low retentivity and low coercivity but high permeability. You want them to be strongly magnetic when the current is on, but lose magnetism quickly when it's off. Soft iron is ideal for cores.
Explains fridge magnets versus scrapyard cranes. Okay, the other side of the coin. Changing magnetic fields, creating electricity, electromagnetic induction.
Faraday's discovery, a cornerstone of technology. His laws of induction state that if the magnetic flux through a loop of wire changes, an electromotive force, MF, basically a voltage, is induced in the loop.
Magnetic flux is like the amount of field lines passing through.
Yeah, more formally B dot A, integrated over the area. The induced EMF is proportional to the rate of change of this flux. Faster change, bigger voltage.
And Lenz's law gives the direction. It seems tricky.
It's crucial and embodies conservation of energy. Lenz's law says the induced current will flow in a direction that creates its own magnetic field, opposing the change in flux that caused it. Nature resists the change.
So if flux increases, the induced field tries to decrease it. If flux decreases, the induced field tries to boost it.
Exactly right. Opposes the change.
Emotional EMF is another way induction happens.
Yes. If you move a conductor through a magnetic field, the charges inside experience the Lorentz force, QVB. This force pushes charges along the wire, creating a voltage difference and induced EMF. For a wire length L moving at speed V perpendicular to field B, MF equals BLV. It's consistent with the changing flux idea, too.
Eddy currents. Those sound less useful.
Often they are unwanted side effects. They are loops of current induced within the bulk of a conductor when the magnetic field through it changes or it moves through a field. They also obey Lenz's law.
What do they do?
They dissipate energy as heat, used in induction cooktops, and create damping forces used in magnetic braking. The text shows a pendulum swinging through a magnet slowing down due to eddy currents. To reduce them, you often use laminated cores, thin insulated sheets, or slots.
But induction is vital for electric generators.
Absolutely. That's how most of our electricity is made. Mechanical energy, from turbines, spins coils of wire in a magnetic field. The flux through the coils changes continuously, inducing an AC voltage. They convert mechanical energy to electrical energy.
The text also covers self and mutual inductance.
Right. Self-inductance L is when a changing current in a coil induces an F in the same coil, because the changing current creates a changing magnetic field and thus a changing flux through its own loops. The flux linkage N phi is proportional to the current I, so N phi equals Li.
In mutual inductance.
That's when a changing current in one coil induces an F in a nearby second coil, because the magnetic flux from the first coil links through the second, essential for transformers.
Transformers use this to change AC voltages.
Yes, two coils wrapped on a core. Changing AC current in the primary coil creates changing flux, which induces an AC voltage in the secondary coil. The voltage ratio depends on the ratio of turns in the coils. The text also knows energy stored in an inductor's magnetic field is U equals 12Li squared.
Power generation, transformers, metal detectors, induction stoves, all induction. Okay, let's focus specifically on AC circuits now.
Alternating current. Unlike DC, the voltage and current sinusoidally reverse direction periodically. The text explains cycles, frequency, cycles per second hertz.
And we need RMS values for AC.
Yes, because the simple average over a cycle is 0. RMS, root mean square, gives the effective value the equivalent DC value that would produce the same power dissipation in a resistor. Standard wall outlets are rated in RMS volts.
How do R, L, and C behave with AC? Resistors are simple.
Resistors are easy. Voltage and current are in phase. They keep together. Ohm's law VIR still holds using RMS values. Inductors resist changes in current. With AC, the voltage across the inductor leads the current by 90 degrees, a quarter cycle. They impede AC flow with inductive reactance XL equals omega, where omega is angular frequency, 2 pi f. Reactance increases with frequency.
Capacitors.
Capacitors resist changes in voltage. With AC, the current flowing into the capacitor leads the voltage across it by 90 degrees. They impede AC flow with capacitive reactance, XC equals 1 omega C. Reactance decreases with frequency.
This phase difference makes combined circuits tricky. The series LCR circuit.
Putting all three in series with an AC source, the total opposition isn't just R, it's impedance Z. It combines R, XL, and XC, but vectorially, using phasors, because of the phase differences, ZIL squared, R2 plus XL, XC2.
And the phase between voltage and current depends on XL versus XC.
Exactly. If XL-XC, the circuit is inductive, voltage leads current. If XC-XL, it's capacitive, current leads voltage. The phase angle phi is given by tan phi XL-XCR.
Resonance is key here too, right?
Yeah, crucial. Resonance occurs at the specific frequency where XL equals XC. At this frequency, the reactive parts cancel out. Impedance Z is minimum equal only to R.
So maximum current flows.
Maximum current for a given voltage, yes. And importantly, at resonance, the voltage and current are back in phase. Phi equals 0. This is exactly how radio tuning works, adjusting L or C to make the circuit resonate at the desired station's frequency.
The text mentions power factor.
Yeah, because V and I can be out of phase, the average power delivered isn't just VRM's erms, it's VRM's cos phi, where cos phi is the power factor. It represents the fraction of apparent power that does real work, dissipated as heat.
And LC oscillations.
Briefly mentioned. In an ideal LC circuit, no resistance, energy oscillates back and forth between being stored in the capacitor's electric field and the inductor's magnetic field, like an electrical version of a mass on a spring.
DC power, radio tuning, all LCR circuits. Okay, brace yourself. Things are about to get quantum weird. The dual nature of light and matter.
Right. Classical physics hits a wall here. The photoelectric effect was a big problem for the wave theory of light.
Light hitting metal, knocking electrons out. What couldn't wave theory explain?
Several things the text highlights from experiments. First, emission depends on the frequency color of light, not just intensity, brightness. Below a certain threshold frequency, no electrons come out, no matter how bright the light.
Okay.
Second, if the frequency is high enough, electrons come out almost instantly. No time delay needed for energy to build up, even for very dim light. Wave theory predicted intensity should be key, and there should be a delay for dim light.
Einstein's explanation, light comes in chunks.
Exactly. He proposed light energy isn't continuous, but quantized into packets called photons. Each photon has energy E equals h nu. H is Planck's constant, nu is frequency.
So one photon hits one electron.
Kind of. A photon gives all its energy to an electron. To escape the metal, the electron needs a minimum energy, the work function, phi naught. If the photon energy window is less than phi naught, nothing happens.
Threshold frequency.
Right, higher threshold phi naught. If nu is greater than phi naught, the electron escapes, and the leftover energy, h nu phi naught, becomes its maximum kinetic energy. Kmax U phi naught. Einstein's photoelectric equation explained everything perfectly.
So light is both wave and particle. But then, matter too. De Broglie's
radical idea. If waves, light, can act like particles, photons, maybe if particles like electrons can act like waves, he proposed a wavelength for any moving particle. Lambda equals hp over momentum.
A wavelength for an electron. Sounds crazy. Was there proof?
There was. The Davison and Germer experiment. They shot electrons at a crystal and observed diffraction patterns. Just like X-rays, which are waves diffracting off crystals, electrons were behaving like waves with the exact wavelengths de Broglie predicted.
Mind blown. So wave-particle duality.
The central concept of quantum mechanics. Everything exhibits both wave and particle properties. Which aspect you observe depends on how you interact with it. Wave nature dominates propagation, particle nature dominates interaction.
The text mentions electron microscopes using this.
Perfect application. Accelerated electrons have much shorter wavelengths than visible light, so electron microscopes can resolve much, much finer details, exploiting the wave nature of electrons.
Solar cells, digital cameras, the fundamental weirdness of reality. All quantum. Let's go deeper. Structure of atoms and nuclei.
Okay, building on quantum ideas. The text briefly reviews models. Dalton's solid atoms, Thomson's electron discovery and plum pudding model, then Rutherford's gold foil experiment revealing the tiny, dense, positive nucleus.
But Rutherford's model wasn't stable classically. Electrons orbiting should radiate and spiral in.
Exactly. Bohr fixed it, incorporating quantum rules, his key postulates. Electrons exist in specific stable orbits, stationary states, without radiating energy. Angular momentum in these orbits is quantized. Only certain values allowed, multiples of h2pi.
And they only radiate when jumping between orbits.
Yes. An electron jumps from a higher energy orbit, E high, to a lower one, E low, emitting a photon with energy exactly equal to the difference, h. E high, E low. Absorbing a photon of that energy makes it jump up.
This explains discrete energy levels in atoms.
Precisely. And why atoms emit and absorb light only at specific characteristic wavelengths, their line spectra. The text mentions the hydrogen spectral series, Lyman, Balmer, Paschen, and Rydberg's formula, which empirically described these wavelengths long before Bohr explained why.
Okay, zooming into the nucleus itself. Protons and neutrons.
Nucleons, collectively. Yeah. Protons, positive charge, neutrons, no charge. Atomic number Z is the number of protons defines the element. Mass number A is the total number of nucleons, Z plus N, where N is neutron number.
The text defines isotopes, isobars, isotones.
Quick review. Isotopes have the same Z, same element, different N and A. Isobars have the same A, different Z and N. Isotones have the same N, different Z and A. Nuclear masses are measured in atomic mass units. The text shows how to estimate nuclear size and density using germanium example. Finding nuclei are incredibly dense.
What holds the protons together against their mutual repulsion?
The strong nuclear force. It's a fundamental force, much stronger than electromagnetism, but only acts over very short distances, basically within the nucleus. It attracts protons to protons, neutrons to neutrons, and protons to neutrons.
In nuclear binding energy. Related to mass.
Yes. Astonishingly, the mass of a stable nucleus is slightly less than the sum of the masses of its individual protons and neutrons if they were separated. This missing mass is the mass defect.
Where'd it go?
Converted into energy when the nucleus formed, according to EMC2. That energy is the binding energy, the energy you'd need to put back in to break the nucleus apart. Higher binding energy per nucleon generally means a more stable nucleus.
Unstable nuclei undergo radioactivity.
Spontaneous decay. Alpha decay emits an alpha particle, a helium nucleus, 2 protons, 2 neutrons. Beta decay emits an electron, beta minus, or a positron, beta plus, as a neutron changes into a proton or vice versa. Gamma decay emits a high-energy photon.
Decay follows a pattern.
An exponential decay law. N equals N naught, E lambda. N is number remaining, N naught is initial number, lambda is the decay constant, characterized by half-life, half, the time for half the nuclei to decay. The text also mentions decay series chains of decays until a stable nucleus is reached.
Gamma decay is often secondary.
Yes, alpha or beta decay might leave the resulting nucleus in an excited energy state. It then drops to its ground state by emitting one or more gamma-ray photons, like atomic energy levels, but nuclear, so energies are much higher.
Finally, the text mentions nuclear energy sources.
Fission and fusion. Fission is splitting a heavy nucleus, like uranium-235, into smaller ones, releasing a lot of energy. That's current nuclear power. Fusion is combining light nuclei, like hydrogen isotopes, deuterium and tritium, into a heavier one, like helium, releasing even more energy per mass. That's how stars work, and the goal for future fusion reactors.
Element properties, carbon dating, nuclear power, medical uses, all tied to atomic and nuclear structure. Last big topic, semiconductors, the heart of modern electronics.
Materials like silicon or germanium, halfway between conductors and insulators. Their magic is that their conductivity can be controlled by doping, adding tiny amounts of impurities.
Creating N-type and P-type.
Right. N-type has extra electrons, negative carriers. P-type has holes missing electrons that act like positive carriers.
Joining them makes a PN junction diode.
The fundamental semiconductor device. It allows current to flow easily in one direction, forward bias, positive to P side, but blocks it almost completely in the other direction, reverse bias, positive 10 side. A one-way street for current.
Used in rectifiers to change AC to DC.
Exactly. A single diode gives half-wave rectification, passes only half the AC cycle. A bridge of 4 diodes gives full-wave rectification, flips the negative half cycle to positive. Result is pulsating DC.
Still pulsating, though. Needs smoothing.
Right, so filters are used, typically capacitors, to smooth out the pulses into something closer to steady DC. Then voltage regulators provide a stable output voltage.
The Zener diode acts as a regulator.
Yes, it's a special diode designed to work in reverse bias. Above a specific Zener voltage, it breaks down safely and maintains a nearly constant voltage across itself, even if the current changes. Great for stabilizing voltage.
Photodiodes detect light.
They do. Operated in reverse bias, the small leakage current, dark current, increases significantly when light shines on the junction, creating more electron-hole pairs. Current is proportional to light intensity, used in light sensors.
Solar cells are related but different.
Similar principle, but designed to generate power, not just detect light. They're large PN junctions. Light creates electron-hole pairs, and the junction's built-in field separates them, creating a voltage photovoltaic effect that can drive a current through an external circuit. Direct conversion of light to electricity.
And LEDs? Light-emitting diodes.
Kind of the opposite of a photodiode. They're forward-biased PN junctions. When electrons and holes are forced across the junction and recombine, they release energy as photons light. The material determines the color. Very efficient light sources.
And the king of semiconductor devices, the transistor.
The invention that changed everything. Usually a 3-layer device, like NPN or PNP. The key idea is that a small current flowing into the middle layer, the base, controls a much larger current flowing between the outer layers, emitter and collector.
So it acts like an amplifier or a switch.
Exactly. With proper biasing, emitter-based junction forward-biased, collector-based junction reverse-biased, as the text describes, that small base current IB controls the large collector current IC. IC is roughly proportional to IB. IC equals beta ID, where beta is the current gain. Tiny input signal controls large output.
And transistors are the building blocks for logic gates.
They are. Logic gates, and ND, or not NAND nor, perform basic logical operations on binary inputs, zeros and ones. They're built from transistors configured as switches. The text introduces truth tables, showing output for all inputs, and Boolean expressions to describe gate functions. These gates are the foundation of all digital computers.
Chargers, sensors, displays, computer chips, semiconductors run the show.
They really do. It's incredible how these principles underpin so much technology.
Wow, that was quite a deep dive. We've gone from spinning bikes and wells and water in pipes, through heat engines and oscillating pendulums, into the quantum realm, inside the atom and nucleus, and landed in the silicon chips powering our world, all guided by this one extensive source.
It really shows the breadth of physics, doesn't it? And how taking the time to unpack these core ideas using the examples provided gives you a powerful framework for understanding so much. It connects things you wouldn't necessarily think are related.
It does feel like a shortcut to being, well, genuinely informed across these huge domains. And thinking back to how this text started, that preamble quote about justice, welfare, liberty, it makes you wonder, How does this kind of clarity, this understanding of nature's fundamental rules we've just explored, how does that actually help us build the kind of world envisioned in those opening lines? Technologically, obviously, but maybe. Yeah, maybe even in how we approach building society itself.
So that's a fascinating thought to end on. The interplay between understanding the rules of reality and shaping our own human structures.